Okay, this is the last section of chapter 3, matrices of relations. A matrix is a relation R from X to Y. Yeah, we may label the rows with the element of X, and we label the columns with the elements of Y. Okay, in some order. If X are Y, then we set the entry in row X and column Y is 1. Otherwise, X R Y is equal to 0. We define an entry as 1 or 0. Okay, this matrix is the matrix of the relation R relative to the ordering of X and Y. For example, if R is a relation like this, for example, 1B is X comes from 1, 2, 3, 4, and Y comes from little a, b, c, d. Then we have 4 rows from X, and we have 4 columns from Y. Okay, so 1B is here. So 1B, which is this position, we mark 1. 1D, first row and first column, let's say 1. And all others are 0. 3, for the third row, 3C, 3B. So C and B are, let them be 1, and all others are 0. And fourth row, 4A, there is 4 and first is 1, and all others are 0s, like this. So if we have 2 sets with the relations like this, then we can define a rectangular matrix, okay, like this, with 0 and 1 only. We can define a relation matrix. We can have a 0, 1 matrix. The matrix of relation R of example 3.5.1 relative to the ordering 2, 3, 4, 1. If we change the order of this 1, 2, 3, 4, then we just switch the row in that order. So we can if we fix, then the matrix will be fixed. If we switch, then row will be changed. If we change the column, if we change the order of columns, then the column will be replaced. So if we just give an arbitrarily fixed order, then we can just continue our argument with that fixed order. So ordering means it's just a change of the orders, change of the rows and columns. Next example, the matrix of the relation R from 2, 3, 4, and 5, 6, 7, 8 relative to the ordering 2, 3, 4, and 5, 6, 7, 8 defined by like this. Okay, 2, 3, 4, and 5, 6, 7, 8. If X, R, Y means X divides Y. X divides Y. Okay, we have these numbers. So if 2 divides 6, then it's 1. But 2 do not divide 5, so it's 0. 2 did not divide 7, so it's 0. 2 divide 8, so it's 1. Okay, 3 divide 5, no, so it's 0. 3 divide 6, yes, it's 1. 3 divide 7, no, so 0. 3 divide 8, no, so it's 0. So 4 divide 5, no, 0. So 4 divide 6, no, it's 0. So 4 divide 7, no, so it's 0. 4 divide 8, so yes, it is 1. So we can form a matrix, 0, 1 matrix from a given relations. Okay. Next, matrix of the relation. There was an errata here. This example is not symmetric. I'm making my own lecture note from the different sources. So you may be able to find the right the errators. That's very natural. So that's the process of creating a new content and new knowledge. So I want you are aware to find out something which is not perfectly clear. Okay, so if no one mentioned it, then I cannot give the best possible credit to none of you. So I expect some of you are aware to get the best possible credit that I can give you with the best, highest level of recommendations for you when you need. Okay, anyway. Here is a matrix of relations are like this. Okay, AA1, AC, so 1, CC, 1, DA1, DC, DC1, DD1, like this. So we have 1, 2, 3, 4, 5, 6, 7. So I think we have 1, 2, 3, 4, 5, 6, 7 ones, and all others are 0. Okay? We have a 0, 1 matrix like this. As you see here, it is reflexive. It is reflexive because it is reflexive. This is not reflexive because here 2, 2. The BB, there is no BB. So it's not reflexive. And here, this is not symmetric because as you see here, here is the DB has 1 here, but BD has no 1 here. Okay, so BD does not imply DB, so it is not symmetric. It's not reflexive, not symmetric. And what else? Anyway, this is example like that. And next, this. Let's define. R1 is a relation from X to Y. R2 be a relation from here to here. Like we define it here. This is also a very interesting example. From these relations, we can have a 3 by 2 matrix like this. From this relation R1. From here, we can define a matrix of R2 of size 2 by 3 like this. What about the product of these two matrices? Product, these two matrices from two distinct relations. Okay, this is a 3 by 2 matrix and this is a 2 by 3 matrix. If you multiply, then what do you have? You have a 3 by 3 matrix like this, which has 0 and 1 and 2 in it. If so now let's think about how we do interpolate this matrix, this product of two matrices. So I want to define a relation, a matrix, the matrix representation of this relation, this composite relation R2 circle R1. But the definition of this relation matrix, it was a 0, 1 matrix, 0, 1 matrix. So if we just replace these 2 as 0, 2 just 1, then this matrix is a 0, 1 matrix, isn't it? So why? What if we just define the relation, the matrix of the relation of these two composite, R2 circle R1, as this matrix, this 0, 1 matrix, then what's going to happen? Then it says, so our conclusion is it will be okay. So now we define the matrix of a relation of this composite of two relation R2 and R1 by just only change all non-zero entries in A1, the product of two matrices A1, A2 to 1. So if we have a non-zero entry, then makes it all 1. Then we define that matrix as the matrix relation of these composite relations. Okay. Then now we not only have a matrix from one relation, we can also find the matrix of many different relations by the composite functions. Okay. So we can have the matrix of the relations composite of many relations, not only 2. We can think about the composite of 3 relations and 4 and 5s as well. Okay, here, with those concepts in our mind, then we can think the theorem 5.6. Let R1 be a relation from X to Y and R2 be a relation from Y to G, choosing orderings of X, Y, and G. Then A1 is the matrix of R1 and A2 is the matrix of R2 with respect to the ordering selected. So let's orders are fixed. Then the matrix of the relation of this composite R2 and R1 with respect to the ordering selected is obtained by replacing each non-zero term in the matrix product A1 times A2 by 1. So this is a so when we define the matrix of the product of relations like this, then it will work. The next example shows this. Let R be a relations. Then A is a matrix of the relations. Then A square, which is a product of these two matrices, will be like this. Okay? Then just replace those non-zero entries are all ones here. So we have for 6 non-zero entries, which and all others are 0 entries. And this matrix is defined like what we had the definitions. So, but the interesting thing is, whenever ij is in A square is non-zero, some ij non-zero, then aij in A's is also non-zero. Do you see here? There are only 6 non-zero entries in here, and there's only 6 non-zero entries here. What's the position? As you see, whenever these are zeros, the corresponding entries are all zeros. Whenever the non-zero entries in here in A square, at the same place, it has non-zero entries in here. So it has a very close relations. What that means is the relation is transitive. Okay, transitive. Okay, whenever ij entry of A square is not 0, then ij entry of A is not 0 also. So it's transitive. It's a property that has. Okay, now the last example in chapter 3, matrix relations. If we have relations like this, relative to the ordering A, B, C, D, E, like this, then A can be defined, the matrix of the relations can be defined as this 5 by 5 matrix. Then A square, which is the product of these two matrices, can be defined in this way. Then the relation matrix is a 0, 1 matrix of this, where all the non-zero entries replaced by 1. Then the entry of row 1 and the column 2 of A square is non-zero, but the corresponding entry, in this case, the corresponding entry in A, here, but in here, in these relations, here, the 1, 1 entry of A square is 2, which is non-zero, but 1, 1 entry of the matrix A is 0. So in this, which means in this relation, this relation is not transitive. So when you check whether a relation is transitive or not, can be done by just matrix product that you are quite familiar. Instead of doing logics and counting all the things, same thing can be decided by just matrix multiplication, isn't it? So now you can change the problem of the discrete mathematics to a problem of matrix product. So you can come and go. So that's the concept of combinatorial matrix theory. So whatever mathematics that you learn, you can use it. You can do the same thing. You can prove the same thing. You can conclude the same thing with the other tools that you have learned. So most of you already have some knowledge on the matrices. So you can use those knowledge to deal with the important concept in discrete mathematics. I think that's the end of chapter 3. Any questions? Mr. 홍석호